Today, I want to talk to you about quantization, and then I'll give you an actual experiment that you can run and go through to formalize this and understand it like on your own in real world terms. I think starting off, I think that people overcomplicate what quantization is. They think of it in lots of different terms, and like they think of it as a like doing more complex things than it does, right? The term quantization in and of itself, it kind of evokes quantum physics and like that you're doing like maybe some crazy math within it. The math for quantization is like as simple and as basic as it could get. Like especially when it comes to AI, right? Like this math is very simplistic to explain and to understand. It's just the term quantization, right? So if you get past the term quantization, what exactly is quantization? Literally all it is it's just essentially like shrinking the dimensions of the weights, right? Like it's so in going to like a standard quantization, so like 16-bit quantization, we just essentially we drop the remainder, right? So if the weights in a model will be like what we would look at on the left hand side typically, right? Like 13.45678, 2.45678, 1.22, 1.154, 11.43, 1.2543, etc. And then we just drop those remainders, right? So 13, 9, 32, 3, 71, 11, 1, 1, 1, 2, and those become the weights. And then intuitively, you would probably think like that has to be like harmful for the model, right? That wouldn't be good overall. Everything within this and everything that is known within the research shows that this particular method has minimal performance decrease to the model overall. Like it's you're talking like singular digits, right? Like so going to 16-bit quantization, you'd be looking at it like, let's call it like a 4% decrease. And then we can shrink these numbers down further from here, right? So we can go down to 8-bit quantization. And then in 8-bit quantization, we do it essentially, we represent like every single number as bigger whole numbers, right? So if we're looking at here, if our floating point number is 1231.4531 is the end one, well, we turn it into an integer, which is 1231, and then we break that down into an 8-bit integer where all of the integer weights equal out specifically to 1231. And then so this is like on the back end, it's just math, right? And it's just math to simplify exactly how you represent this end equation. This 1231.4531, we can represent it very simplistically in 8 bits as 1231. And then within that, we get even more like performance, our performance on our 8-bit quantization. Let's say that quantizing down to 16-bit, it's 96% performant. 8-bit, let's say it's like 94% performant. It's kind of like how that would break down, generally speaking. And then within that, it's like you're getting down to like 4 times less as far as like the storage size of the model, right? And that's the bottom line that this all comes down to. So when all of this comes down to storage size of the model and inference of the model, and that's the bottom line, right? So when you are inferring a model, meaning that you're calling the model, like I want this model to perform things. You want it I want to be able to prompt the model. You need to load the model to the GPU for inference, right? And then so how big the model is depends on how big your GPU is and how much that you need to load onto the GPU. And then so I'll take like a 7 billion parameter model as a general example. So if we're talking about that as a full model, generally speaking, we're going to want at least like 8 gigabytes of GPU just to load that model for inference. For training, we're going to want like 3 to 4 times that amount, right? But To load it for inference, generally speaking, we're going to want 8 gigabytes. But what if we don't have 8 gigabytes available for our GPU? Then we can quantize it, right? So if we quantize it down to 16 bits, all of a sudden then we need 4 gigabytes. If we quantize it down to 8 bits, all of a sudden we need 2 gigabytes. And then what we could, the kind of king of the hill, like what we can get down to, like overall, is I saw it somewhere here. So we can get down, I've shown here to 8-bit, we can get down to 4-bit. So again, a smaller equation, and then we can get down to 2-bit quantization. And then 2-bit quantization looks a bit interesting. I'm trying to find the diagram I saw here that had 2-bit quantization. That's int 8, which is exactly what we're looking at here. 8-bit. Let's do this. There we go. So you have 2-bit quantization here, where essentially, so from 32-bit, let's say that these are the weights, like, 0.2, 1, 0.3, 0.1, minus 1.6, 0.7, etc. And then with 2-bit quantization, it's 1, 2, or 3. 0, 1, 2, or 3, right, is how everything is represented. So it's one of those two numbers. So everything that is within this, so no matter if it's a 0.2, it's represented as a 1. If it's a 1, it's represented as a 3. 0.3 is represented as 2, etc. And that's what happens with 2-bit quantization, right? And then so with 2-bit quantization, it comes down, and it's again just more interesting math, but it's breaking it down. And then what you can actually get down to, like the floor is not actually 2 bits. It's the floor is 1.5-bit quantization. And then 1.5-bit quantization is released by Microsoft, released and invented by Microsoft. And then with with 1.5-bit quantization, their models are still like 90% performant compared to like non-quantized models. And then you can see here, like this, it's the math gets crazy with 1.5 bits. It's everything is represented as either a 0, a 1, or a 0 and 1, and then so that's why 1.5 bit, right? And then within that, the thing is though, with 1.5-bit quantization, the interesting thing is, so at the top I mentioned that you need quadruple whatever the normal GPU load would be to fine tune the model. So let's say that, like, if it's an 8-bit model or a 7 billion parameter model, you would need 8 gigs of GPU for inference, but to train that model, you would need like 24 to 32 gigabytes of GPU, right? Because you need to load like the full model onto the GPU for training, and it's just like it's how much you need in order to train that model overall. And then so with general quantization methods, so like the 16 and the 32-bit quantization, 8-bit quantization methods, you can shrink that down, right? So let's say that it's 8-bit quantization, for example, and then we would need 2 gigs for inference. Then we would need like 8 gigs in order to train it. And then so we could train an 8-bit quantized model on consumer GPU, which is exactly what we're going to demonstrate here for you, right? But so within that, the interesting thing with 1.5-bit quantization, specifically it's 1.58-bit quantization, is that it doesn't follow that same equation, right? It breaks that rule within the quantization method, because you need to be able to train first. You need to do one full training run on the model with the full weights. So if it's a 7 billion parameter model, you need 24 to 32 gigabytes of GPU. Then you can bring it down to 1.5 bits of quantization and do it from there. But you need to have access to a huge amount of GPU to do that first training run for 1.5 bits, and then you can shrink it down from there. Just highlighting that overall with that 1.5-bit method. It's a unique method overall within that. And so we've talked about this theoretically overall, right? Now let's talk and break this down to like, what does this look like in actual real world terms? So we're looking at here at a model, which is a very popular image generation model, image diffusion model, meaning that like text to image, and it's called Flux model, right? And then so Flux Dev is a 12 billion parameter model. And then so 12 billion parameters, you're not going to run this on any traditional consumer grade GPU unless you've got like something that came out literally this year, right? And then like then you have a chance. And then other than that, like no. And then so within that though, what we can do is not only can we run this model and then like run it for inference, but we can also train this model. And then again, training this model, it requires 4 times the amount of GPU that it does for inference for the model. And then so how exactly are we going to do that? We're going to quantize the model overall. And then so this Colab notebook that we're looking at here, this wasn't built by me. This was built by Hugging Face, and then I just happened to find it, and I've been playing around with it, and it's super cool, right? Allows you to do exactly what we're going to go through, which is fine tune a Flux Flux Dev model on consumer hardware and in floating point 8. So we're going to quantize the model to floating point 8, like integer 8, which is exactly how we're going to be able to run this like and do all of this. And then so essentially I've gone through this, and then so as they lay out here, I'll just read it through here. So performing inference is cool, but to make these models truly our own, we also need to be able to fine tune them. Therefore, in this post, we tackle efficient fine tuning these models with peak memory use under about 10 gigabytes of VRAM on a single GPU. This post will guide you through fine-tuning Flux Dev using QLoRa with the Hugging Face Diffusers library. We'll showcase results from an NVIDIA RTX 4090. We'll also highlight how floating point 8 training with Torch can further optimize speed on compatible hardware. And then so we're going to run this all on a T4 GPU in this instance. And then so for the Flux hardware, we're using the Flux model, and then we're training it via QLoRa, and then so QLoRa is the quantized LoRa, right? And then so that's how we're essentially quantizing the model and then quantizing what we need to load within that. And then this is essentially the LoRa equation that we're taking here. So LoRa learns 2 smaller matrices and then updates to the weights the model, essentially. The bottom line is that it's creating projections. I talk about this a lot on my channel, right? Where it's the models don't actually deal with the actual data sets themselves. They're always dealing with like representations or projections of the data set, right? And that's why all of this works. Like how it, like intuitively, and in my head at least, like these kind of methods like shouldn't work very good. And like it's like you're taking like the essence of the model, and then you're just like cutting part of it off. Like you're kind of like lobotomizing part of it, right? But the models are dealing with representations anyway, and then so again they're dealing with lower dimensional representations. Like they always want to shrink, like and like their perfect representation most of the time would be a 2-bit representation. So it's totally fine to bring it down to that level, right? Because the models like they crave overall sparsity of the data set. Like sparsity eliminates noise, and then so that gives them kind of a clearer picture overall. And then so this method, while you would think that it would be like harmful for the model outputs, it ends up being quite good overall. And then so that's just kind of how this math breaks down here. And then so QLoRa is kind of the powerhouse of all of this. So QLoRa enhances LoRa by first loading the pre-trained base model in a quantized format, typically 4 bits, drastically cutting the base model's memory footprint. It then trains LoRa adapters, usually in floating point 16, on top of this quantized base. So that's, again, it's where it's cutting off like all of that remainder. And then this dramatically lowers the VRAM needed to hold the base model. So for instance, in the Dream Booth training script for high dream. 4-bit quantization with bits and bytes reduces the peak memory usage of a LoRa fine-tune from 60 gigabytes down to 37. So the very principle, same principle as what we apply here to fine-tune flux. Second thing within this is that we're using an 8-bit optimizer, so the optimizer itself is quantized, and then of course it's an atom optimizer, right? It's atom W in this instance, and then so standard atom W optimizer maintains first and second moment estimates for each parameter in 32 bits, which consumes a lot of memory. The 8-bit atom W uses blockwise quantization to store optimizer states in 8-bit precision while maintaining training stability. And then so this technique can reduce optimizer memory usage by about 75%. And then so within your optimizer and the attention mechanism, that's where a majority of your GPU usage is coming down as far as just like mathematically within this. Sorry. And then so just knowing that overall is like why that's important to to quantize the optimizer specifically, right? Like if you don't quantize this, like there's really like not a point in quantizing the rest, because this is like where a majority of the like actual gains are coming in on the inference side there. And then the rest is just highlighting out like and going through exactly how this method works, the math behind it, and then we're training the adapter, right? So in this instance, where the original training that they did was for 700 training steps, which took about 41 minutes overall. And then so for this demonstration, they've reduced it down to 200 steps. I ran it. It took like 25 minutes to go through, 20 minutes to train overall. And this is the code to load and train the model. And then so you can see here, right, pipeline memory usage, 8 gigabytes. So we're loading this full model, but we're loading this full quantized model, the 8-bit quantized version of this 12 billion parameter model, which the 8-bit quantized version allows us to load it with about 8.3 gigabytes of GPU total. And then we run it and train it. And then these are the training results on the free tier, right? So this is the base model, and then these are the like it's the training was like on this style, and then so this is like the stylized output that it will generate, and then so like this is like traditional, and then stylized, right? And then so you can get it to, in this instance, train on this particular style, and then for floating point 8. You can do the same thing here, and then this is what you get. And then again, yeah, it was about 25 minutes for me overall. And then these are the results. Like, and then to me, like these floating point 8, so these quantized results here of these images to me are like better than the floating point, than the BF16, the floating point 16, right? Like this is good. Like just highlighting that overall, right? And then so this is then inference with the LoRa. So this is no LoRa, what it looks like, and then we're going to merge the LoRa with the base model, and then boom, like this is the trained LoRa, right? And then so photorealistic images on consumer grade GPU. The LoRa is fully trained on consumer GPU. So QLoRa coupled with the Fusers library significantly democratizes the ability to customize state-of-the-art models like Flux, as demonstrated on an RTX 4090. Efficient fine-tuning is well within reach, yielding high-quality stylistic adaptations. Furthermore, for users with the latest NVIDIA hardware, Torch AO enables even faster training through floating point 8 precision. And then you can share your models and anything that you would like there at the Hugging Face Hub. I'll leave a link to this blog article here for anyone to review overall, and or this collab notebook here for anyone to review and to go through. And then it's like, so this collab notebook is if you've ever wanted to fine-tune your own, fine-tune a model, a diffusion model, and build your and train your own LoRa's, you can do it all within this notebook, all within about 20 minutes. And then you can change the LoRa that it's being trained on, the data set, etc. Just easily swap that out. just make a copy of this notebook here, do whatever you want with it from there, right? And then so super cool overall. Like the biggest thing, like a lot of people think that you need monster amounts of GPU for these things, and then while you do overall, like the like if you want like the 100% best performance overall, then yeah, you need monster amounts of GPU. But if you want 92% performant, and then in like some cases, to me, I'd call it more performant with this, like this floating point 16 here, or 8 here, compared to the 16. Like this is more performant to me and less GPU overall, right? And then so it's easy to do this. It does take a while to run and generate these images on consumer hardware, right? Like it's not going to be like ChatGPT, where it's just gonna load them out. I will highlight that, right? Like if you're running this, like the floating point 8 on like on the card that they're talked about, like the 4060, you're probably gonna like 2 to 3 minutes maybe for some images, like a couple of images to generate and pop out. Just highlighting that overall. It's not going to be like seconds, but it's going to get you very good output and results like this overall. So here you go. Hopefully this gives you an introduction and like kind of eliminates all of the stigma around quantization overall, and then how exactly you can utilize quantization with a real world example notebook here. If you like this type of content, please like and subscribe. Thank you very much.